So the first exercise is to look at some curved mirrors. Now, you might actually have some proper curved mirrors, or if not, you could use the inside and outside of a spoon. But list the effects that you can see for the concave and convex side of each of the mirrors given to you. So, what do we mean by the convex and concave? Well, if it's a concave mirror, then the reflection takes part on the caved in section, and if it's a convex mirror, then the reflection takes place on the outside of that previous surface. So this would be your concave, as it's caved, it's like a cave, like that, and this is convex. Now these are also referred to as converging and diverging mirrors. Let's see what happens to light in each of these mirrors more closely. If we have a look at this concave or converging mirror, what's happening is that the rays hit the surface of the mirror. If we have a look at this particular ray, if we draw a tangent and then a normal at 90 degrees to that tangent, like this line here, we'll see that that reflection takes place towards the focal point, which is here. Now this is using, you might remember, the law of reflection, where the incident angle equals the reflected, or the angle of reflection. Okay, and here it is. Angle of incidence equals angle of reflection. Now, by looking at what happens to all the rays, then you get this pattern of convergence in towards the focus point. So you always have to remember the lines always bounce off towards the focal length in a converging mirror. For a diverging mirror, it's slightly different. The rays hit the surface of the mirror and this time reflect away from that focus. So how can you work out where the focal point is for a diverging convex mirror? Well, by following the reflected angle, or the angle of reflection, and this reflected ray, we can trace it back as if it were coming from the focal point here. So you could follow any ray and mark its direction back to this focal point here. Okay, so there is your diverging or convex mirror. Now, bear in mind this is like the opposite of what we were doing with lenses. If you remember, lenses, the convex were converging. And now here we have convex mirror, diverging rays. That's just crazy. It's so confusing. Well, as long as you remember it's the opposite for mirrors that it is for lenses, as long as you remember that, you'll be fine. So how do we draw our ray diagrams to find the position of an image in a curved mirror? Well, it's very similar, in fact, a little bit easier than for lenses. We still have our first ray, so we take a point on the object here, and we draw the first ray straight, parallel to the principal axis. And when it hits the mirror, it has to, as all rays must, go through the focus point here. So that's your first ray, the one that goes straight and then focuses or goes through the focus point. And then your second ray is a ray that goes through the focus first and then follows the trend but the opposite way. It hits the mirror and then bounces back straight. Now where those two rays meet is the position of the object. And as we can see here, this object is diminished, it's real, and it's inverted, as you can see. If it had been a virtual image, it would have been behind the mirror, as virtual images like to be. Just like with lenses, however, the position of the object with relation to the focus point is very important. So try the worksheet and different variations to find possible image positions. And it's important that you just remember there are two rays needed. So using the two rays, which were the straight parallel down through to the focus, and then the opposite, focus first, and then parallel. Try this for the exercises on your worksheet and see how you do. Here we have a couple of other situations. This one where the object is between that radius of curvature and the focus. Here when we have an object at the focal point, once again we have an image at infinity. And here we have an object which is in between the focal point and the mirror. And here finally we get a virtual image. Another important point to take into consideration is this distance here, which we call the radius of curvature, which is basically the distance from the mirror to the center of the circle. And it's a distance which describes the curvature of the mirror. So this is another fixed point, like the focal point. Our magnification relationships are the same as for lenses. Figure 15.23 shows us that as the object gets closer to the lens, the real inverted image gets larger and further away. But if the object is closer than the focal point, the image is virtual, upright, and magnified. So those are your trends for images and your magnification. We have linear magnification, which is simply the ratio of the two heights, or the ratio of V over U, considering distances. Now, what do we mean by V and U in this case? Well, it's exactly the same. The U value, is from the object to the mirror, and our V value is from the mirror to the image. Okay, so it's important you remember that. Our angular magnification, as with lenses, is the angle subtended to by the image divided by the angle subtended to by the object. There are some advantages to using mirrors over microscopes. Reflecting telescopes, for example, are used instead of refracting telescopes. Reflecting telescopes use mirrors, and they have some important advantages over refracting telescopes, such as there is no chromatic aberration. That's when the colours refract by different amounts. This is because the light does not have to pass through a refracting medium. Because the light is not going through another material, a refracting medium, then there's no absorption of light. Now this is something we'll talk about in the next chapter, and it will make a little bit more sense to you. But light does lose a little bit of its intensity as it goes through a different material. Some energy is lost also because it has to reflect through a material, and that's called scattering. So absorption and scattering are negative effects of using large lenses. And thirdly, is to do with cost. The objective has only one active surface. That means there's only one mirror usually, as opposed to two large lenses. So high quality, large diameter objectives of the right shape are easier and cheaper to produce. Try this question now. When a 3.2 centimeter tall object is placed 5.1 centimeters from a converging mirror, a magnified virtual image is formed. What is the linear magnification? How tall is the image? Now this seems like an intimidating question to start with, but just go back to some simple formulas. I'm sure you'll be fine. hopefully you got initially 1.9 for your magnification and 6.1 centimeters for your final height of the image. So now we know a little bit more about how mirrors work and why we might want to use mirrors. Let's have a look at the two main types of telescopes. So even though using mirrors reduces chromatic aberration, spherical aberration still takes place. The principal reason for this is that large distances from the pole of the mirror, the rays no longer reflect through the focal point. So you end up with this blurry situation here. The way to reduce this is to design your mirror carefully. If you use a parabolic mirror or surface, then the rays that are parallel to the principal axis always pass through the focus here. Okay, so you get that perfect reflection effect through the center focus. So let's have a look at the two telescopes that you need to be familiar with. The first one, Newtonian mounting. These are microscopes where you look through the side here and you can see what's coming in through here, up there. So there's a change in direction of the light. Now the final reflected image appears at the focal point of the mirror. So the image of the lens is at infinity. Okay, so that's an important point to remember. The image is at infinity. Now how do these work? You have a large curved mirror at one end, and the light from very, very far away comes in through the telescope, hits the mirror, and is focused at a point here. Now, that produces a real image, which is then focused through a small eyepiece lens. It's important to note that the rays arrive parallel because they're far away, and the initial image is focused at the focal point for the large mirror. So we have something happening here. This is where our image is being focused. So in this position, V equals F. The second mirror just reflects it to the lens so you can see it carefully. Now, this is what's going to aid our maths. Now, you should realize that that's because our initial distance, our U, for our formulas, is equal to infinity. So therefore, V equals F. Now, this is definitely one of the cheapest types of telescopes and probably the more popular with people starting out in astronomy. They're quite easy to build, in fact. The second type of telescope, which is French, and I'm not going to try and pronounce it in French, the case-grain mounting telescope, is a little bit different if we have a look at a picture. And it's a standard stereotyped telescope where you look through here and you can see space out there. And it's different to the Newtonian in that you're using two mirrors this time. So the light comes from very far away, again from infinity, and it's reflected at a large mirror here to another mirror, which then brings it to your eyepiece lens here. So you've got a converging and a diverging mirror. The second diverging mirror provides extra magnification. And one of the nice things about this one is you can actually look at the image in the direction the light is coming from. Now, the advantage of this is that the focal length of the telescope can be longer than the tube itself, because you can see that you're not focusing the image at the focal point. So you can actually use quite large mirrors. However, the disadvantage of this is that this mirror here does cut off some of the incoming light because it's in the way, and that causes a bit of a lessened effect. And that's almost the end of imaging. So work through the questions and make sure your notes are complete.